All right, here's an example of motion in one dimension. We have a police car catching a red light runner, is the name of this problem. A police car is stopped at a red light when a car passes him running the red light. The car is moving at a constant speed, which we'll call v sub c, and the police car accelerates from rest at a constant rate, a sub p, until he catches up with the car. So the first part, A, how far do the two cars travel before the police car catches up? And part B, how fast is the police car going at that point? Okay, so let's try to visualize what's going on. Our initial condition is both cars are going to be at the same position at the same time. The police car is stopped and the other car passes by the police car, traveling at a constant speed. So he's going to move ahead of the police car. Well, the police car is going to punch on the gas and he's going to accelerate until he catches up with the car. So when he catches up with the car, they'll both be at the same position at the same time, farther down the road. So the first thing we're going to do is draw a diagram and we'll put in the initial conditions. So here I've drawn a diagram. So on the left, I have a rectangle representing the car, and I've put his velocity there, v sub c, which we're not given a number for that, so we'll just call it v sub c. And then we have below him, we have the rectangle representing the police car, and he's going to start with an acceleration, a sub p, which is we're given as constant. Okay, so they're both at the same position, so I'm going to choose a coordinate system and call that x equals 0. And this is when we're going to start timing. So the time equals 0. All right, then on the right side, this is farther down the road. We have the car traveling at constant velocity, and the police car is now caught up to him. So they both occupy the same position, which we're just going to call x, and it's going to be some later time t. All right, so now we've got everything in there. All right, so this is a constant acceleration problem, so we're just going to apply our constant acceleration kinematic equations. We have the initial conditions, both the police and the car in the same spot, and our final conditions, the car and the police are also in the same spot, but some different distance at some different time. We're given the car has a constant speed or constant velocity, so there's no acceleration with the car. And the police starts from rest, so his initial velocity is 0. All he has is an acceleration. So we'll just write down the kinematic equations. All right, so here's the kinematic equations. X sub c is the position of the car as a function of time. So we just have the velocity of the car times time. Since he's traveling at a constant speed, there's no acceleration, and our initial position is 0, so that we just have x sub c equals v sub c t. Then the next one is the position for the police car, x sub p, and since his initial position is 0, his initial velocity is 0, he's starting from rest, he only has an acceleration, so we have x sub p equals 1/2 a sub p t squared. Now, what's the next thing we do? Well, when the police catches up with the car, they'll both be at the same position at the same time, so we just set these two equations equal to each other. The position of the car and the position of the police officer will be the same, so we'll have v sub t equals 1/2 a sub p t squared. And then we can find the time it takes for the police car to catch up with this red light runner. All right, so when the police catches up with the car, the red light running car, they occupy the same position at the same time. So I just said x for the car equals x for the police. And so we have v sub c t equals 1/2 a sub p t squared. I divide both sides by t. I get v sub c equals 1/2 a sub p t. Solve for t, and I get 2 v sub c over a sub p. So this gives us the time it takes for the police to catch up. So if we're given the velocity of the car and the acceleration of the police car, we could plug in the numbers and we'll get a number for the time. All right, now notice the question didn't ask for the time. It asked for how far. But the position of the car we can get from v sub c t. So now we know what the time is, so we can just plug the 2v sub c over a sub p for the time, and that will give us the position of the car, which is also the position of the police officer, and that will tell us how far they both traveled. All right, so how far they go then, we just say the position of the car equals v sub ct, and we put in the time of 2vc over ap, and that will give us how far they went. That's also the same as how far the police went, since they end up at the same position at the same time. Then to get how fast the police car is going, we just use the velocity as a function of time. The velocity equals a sub pt for the police car, because he started from rest, he had no initial velocity, and we just plug in this time for t, and so we get the velocity of the police car equals a sub p times 2v sub c over a sub p. Notice the acceleration divides out, and we get that he's going twice as fast as the car. It doesn't matter what the numbers are, he's going to be going twice as fast as the car. Isn't that interesting? So if we were given numbers from the problem, now we can just plug in the numbers and get the actual values. But I think what's interesting is that no matter how fast the police car is going or how fast his acceleration is, when he catches up, he's going twice as fast as the car. Hi, Dr. C here. Thanks for viewing this video, and please help support this channel and subscribe. Also, please leave your comments, questions, or suggestions, and I thank you for your support of this channel. I've also included a link to the next video in this series.